I will begin with a word of prayer. Dear Father, we thank you for this day again, Lord. Thank you for the students, and we thank you for the weekend that's about to start, Lord. In your name I pray. Amen. Let me start with my daily quiz problem, which is also known as problem what from the math battle? Problem 9 from math battle? Or AKA what? 119. Okay. Okay, so we were supposed to calculate the flux of this vector field basically through this guy, right? And so it was z is 4 minus x squared minus y squared, where z is greater than or equal to 0. That surface, upward oriented, right? And so, and this is open down here, okay? If I asked you to calculate the flux of the vector field through that surface and the disk at the bottom, at that point, I think the divergence theorem would be a smart move. If your surface is a closed surface, right? If it's bounding a simple solid, then the divergence theorem is a nice tool. But here, I felt like direct calculation is probably a smart thing to do, so I did that. So here's the parameterization of that, which was nice. If you didn't do that, if you just used the graph, then you would find yourself changing the polar coordinates when you got to the integration. So either you change the polar coordinates at the integration, or you parameterize it like this to start with. I mean, it's give or take same calculation basically. Anyway, so in my way of thinking, this is the normal vector field. So then I just calculate the surface integral directly like this. You take the dot product, and I got 64 pi over 3. Any questions? Yeah.
This might be a really stupid question, but why don't you use the R theta dr? Why don't you just use theta dr ds?
Because this is a theorem that we have that to evaluate the flux, to calculate the flux, we take basically the normal vector field times the du dv, so to speak, or if you like, partial x, partial u, cross partial x, partial v du dv. But here the u is theta and the v is r. So it goes back to the foundation of what flux was. As I think about this, I think the divergence theorem is actually kind of cool to think about here. But anyway, more on that later. Because you notice that, what's the, I was just thinking, it's kind of a neat example in the sense that if you look at the vector field down here, what's f of x comma y comma 0 equal to? Z equal to 0, right? So what's the ds down here? Minus z hat, right? Dx dy. We could use that for it. So what's the flux of that vector field through the base? If we take the dot product of the vector field evaluated, the parameterization on the base of the disk of the down here, right? With this ds, I mean this is 0, 0, minus 1 dx dy, right? So look at these two. They're perpendicular. When you take the dot product of those to calculate the flux, you get 0. There's 0 flux through the base if you were to think about it. And so what that says is that this is equal to, well, the integral over the boundary of the gumdrop, right? You see what I mean by gumdrop? It's this kind of shape, right? Ever seen those stupid candies? Kind of looks like that, right? So the boundary, which includes, of course, the flat bottom and the curved top, but then the divergence theorem says, hey, that's the triple integral of the divergence of f over the volume of the gumdrop. So you could have also gumdrop, not a thing, D. Anyway, so you could have taken the divergence of this vector field and just calculated the divergence of that over this region just as well. That's another way you could have calculated the flux if you thought about it that way. That's a kind of sideways way of thinking, though, isn't it? Anyway. All right, so here, next up, I asked you guys to calculate the curl of xy, z squared, xy, z. What do we got? So we got an xz minus 2z. I like it. And then what we got? 0 and minus yz. All right, still good. And 0 and... All right, I think we have a winner. So there you go. That's the curl of that vector field. Now, is that the curl of a vector field? I mean, I'm asking you a really dumb question right now. This vector here, field right here, G, is this the curl of a vector field? Well, yes. We just calculated it, didn't we? So in contrast to problem 7 on the math battle, or the corresponding problem in the homework, that is a curl of a vector field. So at least the starting point of problem 2 makes sense. Right? So I haven't asked you to calculate the flux of something that's not a curl. This is a curl. All right? Whoa. Okay. All right, so you just reiterating that that's the curl. Yeah. So I guess you guys are just trying to calculate it directly. Is that right? That's what it looks like to me. Yeah. Now, I don't know what this means right here. Okay, so I had in mind something trickier than this. Let me show you. So I'm assuming that this was supposed to be the integral over the side, right?
Which one?
This one?
Oh, yeah.
So over the side, we should be putting, if you're going to do that, then using z and theta is fine, but then we also need to put in what these are in terms of everything involved here. So, like the z's are fine. R is equal to, basically the point is, x is equal to cosine theta, y is equal to sine theta, z is equal to z, since r is equal to 1 on this part of it. Yeah? So to calculate this surface, the surface integral around the side directly, this is not bad. I mean, that's yes, that's correct. Yeah, it's good. But this right here needs to be rewritten in terms of just theta and z to go forward. Maybe you know that, and I just cut you off. And this r hat, you got to understand what that is, right? If you're going to go this path, that's cosine theta, sine theta 0, right? So you're going to have to take the dot product of that with these things, with these plugged in, and so forth. This over here was going to be the top part, right? So here, you're working where 0 less than or equal to r less than or equal to 1, 0 less than or equal to theta less than or equal to 2 pi, and z is 1, right? Now, if this, I'm looking at right here, and I can't tell, but I think you're saying r dr d theta z hat, is that right?
Yeah.
Good. That is, in fact, the correct ds for the top. All right? But again, this, you have to plug in the appropriate formulas for x and y and z. Z is easy enough. The z's are 1. But x, would be r cosine theta, y would be r sine theta on the top, right? If you're going to go this path, right? Anyway, I don't want to do all that, so let me try to show you an easier way. I hope an easier way of doing this problem in its entirety. So the idea of this problem is that if we take S union with S naught, all right, where S naught is this piece right here, oriented downward. The downward oriented disk at z equal to 0. Unioning that to S, if I take S union that, I have the boundary of a closed solid cylinder, right? So this is equal to the boundary of a cylinder. Let me call that cylinder E just to give it a name. Here E is x, y, z such that what? X squared plus y squared less than or equal to 1. 0 less than or equal to z less than or equal to 1. All right? Now, the reason I'm interested in E is because E is a simple solid. And a simple solid is what I can apply the divergence theorem to. Right? So, divergence theorem says that the triple integral over E of the divergence of the field in question, which in this case is the curl of F, that's equal to the flux of the curl through the edge of the boundary of E. Now this time, since I constructed the curl correctly, because I had you guys do it in the previous problem, so I can't mess it up, either through application of the general vector identity that the divergence of the curl is 0, or through straight calculation, take the divergence of this vector field, what do you get? What do we get? We get 0, right? Because we get z minus z plus 0, which is 0. So the divergence of that curl is 0, which means that this volume integral is straight up 0. But on the other hand, the boundary of E, right, is S plus, so we have the surface integral over S of the curl plus the surface integral over S naught of the curl. One of these is a pain to calculate. One of these is actually pretty easy to calculate. Yeah.
This is a really simple question. How do you read S? Is that S plus S naught?
This is the union. Yeah, I mean, admittedly, it's something a little bit more esoteric than that, but it's essentially a union. I mean, it's a gluing together of surfaces. I'm keeping the orientations of the parts as well. All right, so this is what we want, right? And this is pretty easy to calculate. I hope. That was my hope. What is S naught? What is S naught? S naught is, can we describe it? It is, we could say x squared plus y squared less than or equal to 1, right? Z equals to 0. What's the curl of F evaluated at S naught look like? we just look at the curl of f. What happens when we put z equal to 0 in here? 0, 0, minus x, right? I just want to do that before I do much more calculation. If it worked out to all zeros, then I wouldn't have to do anything more. You know? But fine, there's a pesky minus x there. What's the ds here? Minus z hat dx dy, right? So that's actually the part that it could in principle give us something non-trivial, right? If you really understand things, you know it's 0 already. I should say if you have a really good understanding of what's going on, you'd understand it's 0 already. But you might not be there yet, and that's okay for today. Let's see here, S naught, and, oh, let me rewrite that. That's really the integral of x squared plus y squared less than or equal to 1 of 0, 0 minus x dotted with what? 0, 0 minus 1 dx dy. In other words, what we're looking at is the double integral of the x function dA over x squared plus y squared less than or equal to 1. And I claim that that's obviously 0. Because we're integrating x over the whole disk, so you got the left half being negative, the right half being positive, or vice versa, depending on whether or not you count the minus there. That integrates to 0. If you change to polar coordinates, you're looking at the integral of r squared cosine theta, dr d theta. As you integrate over theta, you've got sine theta integrated over 0 to 2 pi. That works out to 0. You get the details. That works out to 0. And that's important because that is also equal to minus the integral of s, which is what we're after, right? So we just worked out that minus what we're interested in works out to 0. Consequently, the answer is 0. Which isn't to say that both of the things you were calculating there were 0. They could have been equal and opposite and canceled out. I just don't know. All right? Anyway, enough about that. Okay, so problem 3, we're supposed to find the flux of this vector. Any questions, actually, before I go on? Again, the big idea here is if you're asked to find the flux over part of a simple solid, right, and the part that you're tasked with you don't like, you take the complement of that part of it, and that gives you the other part of the boundary to the simple solid. So that the flux of that is going to be minus the flux of the other part if the divergence of the vector field throughout the solid 0. Now, if the divergence is non-zero, there's still a relation, but it wouldn't just be minus. You'd have to actually, you know, what if this hadn't worked out to 0? What if this had been 10? You know, if you can imagine this worked out to 10, then we would have just found that if the sum of both of them is 10, and this one works out to 0, well, then that would have said the thing we're after was 10, right? So there's another version of this problem where the divergence doesn't have to be 0, and it's still interesting. The point is that the divergence theorem gives us this relation between the flux of different parts of a simple solid. All right, enough. Any questions about problem 3? You guys have been looking at it for a little bit. Again, we're going to use divergence theorem. So surface integration directly is no fun because there's two pieces. There's a spherical piece and there's a conical piece. So why not trade the integral over the boundary of the snow cone for a triple integral of the divergence of the vector field, right? So what you're looking at here is this, which is, by the way, integral of f dot ds is equal to this, right? And we should probably call this thing E. So this is the boundary of E, this is E, and then details. So the details, this snow cone, we have 0 less than or equal to phi less than or equal to pi over 4. We have 0 less than or equal to theta less than or equal to 2 pi. we have 0 less than or equal to rho less than or equal to r. You pick any point in the snow cone, and it's described by that set of inequalities with spherical coordinates. Clearly, you want to calculate this triple integral in sphericals. If you don't use sphericals on this problem, I kill you. All right. On the other hand, if you have a linear problem on the next test and you use sphericals, I also kill you. Like on the last test, I had to calculate the volume bounded by the plane and the coordinate planes, and two of you, at least two of you that I remember, I don't remember who, I just remember two of you because of your infinite suffering, decided to use spherical coordinates to calculate this volume. No! You must use the right tool for the job. This is a spherical boundary. So, I mean, spherical coordinates make a lot of sense. These. All right. Anyway, what are we looking at here? And the divergence of f, is, as he's pointed out, 2 plus 2z, right? I think they're right, absolutely right about that. So when you put that into spherical coordinates, that's 2 plus 2 rho cosine phi, right? And so that's where this 2 rho plus 2 rho cosine phi is coming from. What's this rho squared sine phi d rho d theta d phi? What's that? That's your volume element, right? The volume element is rho squared sine phi d rho d phi d theta, whatever, however you want to order them. So totally on board with that. What happens after that point, I'm not sure if I can commit to or not. I mean, I know the answer at the bottom is wrong because it's got a theta in it. Oh, you ran out of time. Okay. Fair enough. So, no judgment. I mean, no judgment anyway. But so okay. So you multiply through. You get your 2 rho cubed cosine phi sine phi. Then you get your 2 rho squared sine phi, right? And what's this? So then, I mean, you have some floating expressions here. I know time pressure. All right, I'm just going to, I don't think you're wrong. It's easier for me to. Okay, so integral 0 to pi over 4, great. Integral from 0 to 2 pi. Integral from 0 to r. And like you said, we have 2 rho cubed. I should have kept your integral curses. 2 rho cubed cosine phi sine phi, and then plus 2 rho squared sine phi, right? D rho, d theta, d phi. We've got no function of theta whatsoever, right? So we can drop the theta integration and pull 2 pi out. The rho integrations just give us 2r to the 4th over 4 cosine phi sine phi plus 2r cubed over 3 sine phi. And we just got the phi integral left to do. This, of course, is what? This is really, there's a, I mean, we got to do these integrals, so what do we got? R to the 4th, integral 0 to pi over 4, cosine phi sine phi d phi plus 4 pi r cubed over 3, integrate from 0 to pi over 4, sine phi d phi. Let's see here. If we let u equal sine phi, well, anyway, this is what? Sine, I think it's sine squared phi over 2, evaluated from 0 to pi over 4, am I right? If we differentiate sine squared phi, do we get back sine cosine? Yeah.
What happened to the pi with the first term, the R4? Shouldn't it be pi R4?
Oh, yeah. Thank you. Phew. Okay, I was worried it was something more nefarious. Okay, good. Yes, thank you. Very much so. So the first term is pi r to the fourth over 4, I believe. And then plus 4 pi r cubed over 3 times 1 minus 1 over the square root of 2. Because the 1 over square root of 2 squared gives me a half, the half times a half gives me a 4. Yeah. And sine of 0 is 0. Anyway, details. But the larger point here, does this calculation make sense to you? The big idea? Calculating the flux of the vector field through the edge of a simple solid. So this is just yells at me, use the divergence theorem. I'll come back to this one in a second. Let's look over here at this one for a sec. So problem 5, I think I'm not sure I've asked that exactly in your home. I mean, I've asked bits of that in your homework here and there. I'm not sure I ever got around to putting a dedicated problem in your homework to this, but this is another kind of problem I sometimes ask you guys at this point in the course, which is if you've got a vector field, can you write it as the gradient of a function plus a curl? Now, the choice of f and a are far from unique, but what I do when I'm faced with like this is I try to pick off a piece which is obviously a gradient. So like x squared, y squared, z squared. That's clearly something you can pick up with a gradient, because if we look at 1/3 x cubed, 1/3 y cubed, 1/3 z cubed, well, the gradient of this function is everything here except for that pesky z in the middle, right? So then your problem just becomes, can you find a vector field A such that the curl of A, right, the curl of A is equal to just that z in the middle? And then, so let's see, what did they do? They wrote down the generic formula for the curl, and then they came up with this vector field. How did they do that? So John, how'd you guys come up with this A, 1/2 z squared 0? 0. How'd you get this? So you wanted these to be 0, right?
Yeah.
And you wanted this to work out to just z. So you decided that, maybe you decided that you were going to make this 0 and 0? Or did you start with the x component? Oh, you started with this. Oh, you just, so the easiest thing would be to make that produce the z and then make everything else 0 if you can. Yeah, that's also how I solve these, which is basically just through guessing. So is this the only answer for A? Far from it. You notice that if I was to take A and replace it with the given A plus the gradient of any function you like, any little g, any one, any function, then the curl of A plus the gradient of g is still equal to the curl of A, because the curl of a gradient, as we worked out, is 0, right? So there is stupendous freedom in your choice of A here. You could take his answer and add the gradient of any scalar function, and it would still work. Whew, that's a hard problem to grade, isn't it? Not just any answer. I've got an infinite bunch of answers that don't look at all alike either. Right? So it's a hard one for me to grade. It's not likely to be on the test, but I'm just saying. Maybe. Might be a bonus question. All right, so problem 4 finally is what we're left with, right? So what's going on here? We're asked to calculate the integral along this curve. So this is yet another one of these sort of complementary use the theorem problems. And what I mean by that is the trick here is to go, wait a minute, if I just do this, then I have a simply connected region and I can apply Green's theorem to that, right? So the integral, so this would just be equal, well, not C anymore, but C union with the dot, 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 which I should give a name to, say C3. So C union C3 is the boundary of R. And I know Green's theorem says that, you know, the integral around the boundary of R of p dx plus q dy is equal to what? Integral over R of qx minus py dA, right? So my question, and these might be right. I haven't processed this yet. So what did you guys do? You just parameterized the curves and worked it out? Or did you do what I'm saying? Uh-oh. So why should the sum of those integrals be minus pi over 2? So this what I'm looking at right here, this is a parameterization of C1, right? Right? Yeah. And so, okay. And you said that that works out to 0? Okay, and then what's C2? Why should C2 be equal to this, though? Oh, okay, okay. So do you see the error of your ways, though? Because we need C2 to be the boundary of the simply connected region. C2 is just the upper half circle, right? I need C2 union the line segment, the diameter, if you will, to the circle there. That would be the C2. Okay, so I'm going to... But the larger point here is what's the integral along C3? Oh, I shouldn't have erased that because it was actually relevant. We're about to see why it wasn't wrong that I erased it. Oops, sorry. C3 has what? This is C3. What can we say about C3? C3 has x. Basically, we could say x equals to t, y equals to 0. So dx is dt, dy is equal to 0. This describes C3. So what's this equal to? That's 0. Y is 0. dy is 0. This is 0. Actually, the same logic as y. The integral that you calculated along C1 is 0. Because the differential y is 0, and the dy is, the coefficient of the dx is 0. So in short, the integral around the boundary of R of p dx plus q dy is equal to the integral along C of p dx plus q dy because the integral along the lower line segment is just 0. And so that's great because this is also equal to the double integral of partial q partial x, which is what? 2x and minus what? Minus py, which is minus 1. So we just have to integrate 2x minus 1 over the half circle, right? The 2x term integrates to 0, and that integrates to minus pi over 2. There you go. which is, you guys worked harder to do that, but that's what you found. I remember there was a minus pi over 2 I erased, am I right? Yeah. I know that the x integrates to 0 because we're looking at the half disk, which has got half positive x and half negative x. And the other one's just the area. The area of a half disk is pi over 2, unit disk.